Well, good afternoon and welcome to this session on quantum. Delighted to see you all here and to be back at Slush again. Now, the cliche about quantum computing is that it's the technology of the future, and it's always going to remain that way. Trying to get 1 million qubits to line up in the right way is like trying to herd 1 million cats.
Yes.
But the future might be arriving a lot faster than we think. And quantum is having a bit of a moment. Lots of investment is going into the sector. There's surging share prices of the listed companies like Rigetti and D-Wave over the past year. And companies like PsiQuantum are making some very bold claims. So Mark, tell us, why is there all this excitement now?
Well, John, it's a pleasure to be here. And yeah, it's a really, really exciting time, I think, for compute in general, and particularly for quantum computing. We've seen huge progress in quantum computing over the last 6 months, over the last 12 months. And people are now starting to really wake up to the reality of the fact that quantum computing, it's much closer than people ever thought it was going to be. And so it's reminiscent of the excitement that was, I guess, in the 1970s when everyone was getting very excited about personal computers. I see that bubbling up through AI and through quantum computing. And the way to think about quantum computing is it's the next revolution in compute technology after AI. It computes in a completely different way to the way that we do computing today. It harnesses certain properties of physics, quirky properties of physics, to enable a calculation that is exponentially faster than anything that could be achieved with any classical computer. Even if you turned the entire planet into one giant AI supercomputer, even relatively early stage quantum computers could solve problems that machine could never solve.
So can we delve a bit deeper into that? What can quantum computers do that classical computers cannot?
So what quantum computers do is they harness these properties of superposition and entanglement to do this exponential compute. And that allows it to effectively compute simultaneously in many different possibilities at the same time. So these weird properties, the property of superposition, means that a particle can be in multiple places at the same time. So if I was a quantum particle, I could be here on stage at Slush, and I could be doing my daily jog at the same time. And that sounds very, very weird and counterintuitive, but this is how quantum particles really behave. There's this other property called quantum entanglement. That's even more weird. Einstein described this property as spooky action at a distance and never really believed it himself. But this is the idea where you have two quantum particles. If you entangle them, no matter how far apart you separate these particles, there's always some communication between them. There's some properties between these particles that we can't explain with conventional Newtonian physics. So quantum computers tap into these quirky properties. We build these systems that are very delicate, that tweeze out these unique quantum properties and allow us to do computation using them. And what this does is allows you to access a computational space that is forever outside the zone of conventional computers. And that is in many areas of science and technology that we've found algorithms and applications that would have this exponential power for quantum computing.
Can you tell us, what does it mean for the people in this audience if we get a quantum computer, a fault-tolerant 1 million qubits quantum computer, people are saying by 2027, but certainly by the end of the decade? What will that mean for people in the room? How will they be able to use it, and what will it be able to do?
Yeah, so the early stage quantum computers are uniquely positioned to solve problems in the physical world. So to do advanced simulations across chemistry, across material science, pharmaceutics, catalysts, novel fuels, novel technologies. I think one of my sort of personal hopes for quantum computers is that we will use quantum computers to develop really radically new technologies. One example could be, for instance, room temperature superconductivity. Right now, we don't understand how superconductivity really works. Our models are very crude and rudimentary and do not really predict accurately the properties of superconductivity. And we certainly can't use them to design high temperature or room temperature superconductors. But a quantum computer would allow us to be able to unravel the mysteries of superconductivity, design new superconductors that would absolutely revolutionize technologies across fast, efficient electronics, the way we generate power, the way we distribute power, the way that we store power. You could make compact portable MRI machines. Just unlocking that alone would be a whole new industry in itself. And then you map that to other areas of physics, chemistry, and technology areas, and quantum computing can unlock and massively accelerate humanity's ability to innovate and develop new technologies.
So tell us a bit more about PsiQuantum. There are lots of different quantum computing companies that are trying to use different modalities to get there. There's superconducting, as you're talking about. There's topological, trapped ions. You're using photonics. Tell us about why you have gone for this approach and how it fares relative to the other modalities.
Yeah, so there are many different ways people are trying to make quantum computers, and almost any quantum system that you can isolate and control, in principle, in theory, could be used to make a quantum computer. Now, at PsiQuantum, we're rather unique in that we've gone down the photonic approach to quantum computing. And what this basically means is we use light. We take the individual particles of light that are called photons, and we've figured out how to generate these quantum photonic particles, how to manipulate them, how to detect them, but crucially, how to do all that on a standard silicon microchip. And what we've done at PsiQuantum is we've leveraged existing industry technologies to be able to move as fast as possible. So a couple of examples there. We, very early on in the start of the company, we partnered with a mass semiconductor manufacturer called Global Foundries. These are one of the world's largest semiconductor fabs. You will have microchips inside your phone and your iPad and your laptops that are manufactured by this foundry. And we worked very closely with them, and we were able to bring our quantum photonic process into their foundry. And that has allowed us to produce this very high-performance, mass-manufacturable platform on which we can build and scale our quantum computer. And it's not just the semiconductor chip manufacturing that we're borrowing. We're leveraging the entire supply chain of the semiconductor industry. So the way that you test your devices at scale with high throughput, the way that you then take your photonic chips and you package them with the electronics, with the photonics, make them into assemblies, the way you take your assemblies and assemble them into racks. And we're really leveraging everything that has been done to enable AI supercomputers to be built, but doing that in the quantum photonic domain. And then it goes beyond that. With quantum computers, you may know that they have to be quite cold. One of the advantages of a photonic approach is that it doesn't have to be anywhere near as cold as the other types of computing technologies. So superconducting qubits operate at a temperature that's about 100 times colder than our temperature. We're operating at about the same temperature that a particle accelerator operates at. And that means that we can leverage all of the decades of development of the infrastructure developed by particle accelerators and the cryogenics that they offer to accelerate the ability for us to scale. And so we have some great examples of that, where the Stanford Linear Accelerator in California, we partnered with the Stanford Linear Accelerator to tap off a small fraction of their cryogenic facilities to do some of our early prototype systems. We have a R&D site in the northwest of the UK where we are partnered with the STFC National Laboratory. They also have large cryogenic capabilities for making particle accelerators. And again, we've partnered with them. We're using their existing infrastructure to develop a completely new way to cool and scale photonic quantum compute systems.
Now, that's a very kind of eloquent exposition of how we're going to get there. There are a number of skeptics about the speed at which we're going to get there. And one of them actually wrote in the FT today, John Martinez, who's a very distinguished quantum scientist who won the Nobel Prize for Physics this year. And he pointed out that between 2019 and 2025, Google's quantum chips went from 53 to 105 qubits, a factor of 2 increase in 6 years. And he wrote, "At this pace, I will be long dead before we hit the 1 million qubit mark." So what is he missing?
Yeah, I mean, his observations are spot on. Everyone focuses on qubit count, and everyone's got 5 qubits, 10 qubits. Google are now at 100 qubits. And the end goal is 1 million qubits. So whether you're at 5, 10, or 100, you've still got a really long way to go. And it's that gap that is the missing piece. How do you go from these handful of qubits, which pretty much everyone has, to this regime of 1 million qubits? And if Google keeps at this pace of doubling every 5 years, it's going to take a very, very long time. At PsiQuantum, we took quite a contrarian approach to this, where from the very, very start of the company, 10 years ago now, we knew that you had to scale to 1 million physical qubits to get useful quantum computing. And so we set up the company such that every engineering decision that we made, every strategic decision that we made, was all about how do you enable a scalable technology platform. Mm-hmm. And that's what we've unlocked with the photonic technology. We've unlocked a platform that can go from very low qubit numbers to very large qubit numbers by leveraging the way that we scale AI data centers. You saw Elon Musk built the world's largest data center in 127 days, right? With his 100,000 GPU cluster. Right? And that's what we're tapping into. And so the unique thing about why photonics can scale is because we use optical fibers to allow us to move our qubits between systems. So these are the same optical fibers that wire up the entirety of our global internet system. And so what we can do is use these fiber optics to create a distributed computing system and scale up by having many, many compute modules that are optically and electronically connected together.
Yeah. And where I suspect you would agree with Martinez, he goes on to say that the moment for foundational scientific discovery needs to give way to the era of industrial manufacturing.
Absolutely.
We have much of the physics, now we need the engineers and technicians. Is that right?
Yeah, and for us at PsiQuantum, it's been an engineering challenge for the last decade. We did all of the wacky science as professors in the universities of Bristol and Imperial College, and it was the founding of the company was when we wanted to really bring in the hard-nosed engineers that can solve the really tough engineering challenges. That's why we set up the company. The science was done, it was an engineering challenge, and so, John Martinez, Nobel Prize winner, is writing about it today in the FT, but we've been doing it for the last 10 years.
Okay. I'm always intrigued by the financial argument for quantum computing as well. I find it very difficult to imagine how you can sit across a table from a VC and say, well, we're developing this amazing quantum computer that's going to revolutionize the world. We have no idea actually when it's going to be operational, and it's an unbelievably wicked physics problem and an engineering problem, as you're saying. So how do you convince investors, and how do you show them that you're on the right path, and what are the milestones that you use to convince them you're going to get there?
So it's a very visionary challenge that we have. The quantum compute technology, it will radically change the way we think about compute. And it's very hard to put a value on something like that, but our investors are really bought into the vision of changing humanity for the better, and the understanding that building this technology will have huge benefits for humanity and for the investors. The value that it can create is just uncalculatable at this point in time. And the way that we've convinced the investors to invest in us in the early days and continue to invest in us is our clear vision and mission that has been unwavering since the start of the company. The understanding that you need this large 1 million qubit system, understanding that it's a hard engineering problem that's going to leverage existing capabilities, but pushing existing capabilities right to the edge of what's possible. And we've brought them along through that mission and that vision with them, and the investors can see the continual progress that we're making, the really hard engineering challenges that we're making, and they can see the light at the end of the tunnel. They can see that as we continue on this path and we march consistently towards the end goal, they can see that we will get there.
Mm-hmm. And to date, if I'm right, you've raised about 1.7 billion, and you had a very big raise this year, wasn't it?
We raised $1 billion this year.
What scale of further investment are we talking? Are we going to talk about several billions of dollars to get to fully deployed quantum computers? How big is the investment need?
So these systems that we're building are of the size, scale, complexity of supercomputers. Maybe not the very, very large AI data centers, but it's that level of infrastructure that's required. So we're working very closely with governments, with partners, with investors to enable all of the critical infrastructure in a timely fashion that will allow us to roll out and deploy these systems. So as an example, last year we partnered with Australia and the state of Queensland. They backed us to the tune of $1 billion Australian to build out our first large-scale compute system in Brisbane. And that will be deploying large-scale cryogenic capabilities to provide the basic infrastructure in which we can scale up our systems. Similarly, in the US, in the state of Illinois, there is the quantum and electronics, microelectronics park backed by Governor Pritzker. He's committed $500 million US to that park. PsiQuantum is the anchor tenant there. And we broke ground just last month on our first site out there, which again will be a large-scale system deploying large-scale cryogenics and the critical infrastructure to scale. So we're talking big projects here, big infrastructure that's needed.
But as you were saying, it was the government that's been kind of priming this industry, but is it now the private sector that's ready to take over?
It's both. It's going to take public-private partnerships to make these things happen.
Okay. Now, one thing that people always talk about with quantum is Q-Day, this day when a quantum computer will be able to crack the encryption methods that we have. And I still find this an extraordinary concept, but in 1994, Peter Shaw, a mathematician, wrote an algorithm for a quantum computer that still doesn't exist, that would crack the most commonly used RSA encryption system we have. I actually interviewed Peter Shaw for an FT Tectonic podcast, and he had written a limerick about this. So I'm going to have a short poetic interlude in this session. He wrote, "If computers that you build are quantum, then spies of all factions will want 'em. Our codes will all fail, and they'll read our email till we've crypto that's quantum and daunt 'em."
Oh, I love that.
So how can we best prepare for Q-Day, and when is your best guess about when it might happen?
Yeah. Peter Shaw is an absolute legend in the field. I think if Peter Shaw hadn't made that breakthrough of that algorithm in 1994, we wouldn't be here today. Quantum would maybe not even be on the radar. It was that understanding of the fact that you could do something a conventional computer couldn't, and that something was crack everybody's codes and read everybody's emails. That certainly got people's attention. So Q-Day will arrive. Quantum computers will get to the point of complexity and computational power where they will be able to crack all of today's current public key encryption systems. That's the bad news, right? The good news is that it's going to take a very, very large quantum computer to be able to do that.
How many qubits do you think would be needed?
Oh, I mean, in the tens of millions of qubits to be able to do that kind of problem. And so we will have useful quantum computers solving meaningful problems across science and technology, creating new technologies, generating revenue, having serious impact way before Q-Day happens. And so we will be forewarned when you start to see people using quantum computers to solve really genuinely important problems. Then you can think, right, well, maybe Q-Day is actually 5 years away, maybe 10 years away. And that's when you should start to worry, right? But the other good news is that there are algorithms that people have developed. We call them post-quantum cryptographic algorithms. And these are algorithms that are resistant to quantum computing attacks. So some government organizations are already transitioning their encryption systems over to these post-quantum cryptographic algorithms. Bitcoin and the likes can transition to these post-quantum cryptographic algorithms. So once people really see that quantum computing for sure is on its way, I think there'll be this mass transfer to these more complex and more power-hungry algorithms, but safer algorithms. And I think the real worry right now for people is that the data that you have secret now might not be secret in 10 years' time. People are already harvesting and storing lots of encrypted data right now on the understanding that, in 10 years or so, maybe they'll be able to use a quantum computer to crack and get access to that information.
So that is something that people ought to be worrying about right now.
Right now.
Store now, decrypt later threat.
Exactly.
Yeah. And you were mentioning their cryptocurrencies. I'm always intrigued by this because Bitcoin is supposed to be an immutable record.
Yes.
But if you crack the encryption for it, it suddenly is not immutable anymore.
Not immutable.
So how well advanced is the kind of cryptocurrency sector in thinking about this problem and forestalling it?
It's maybe not as advanced and moving as rapidly as you think. There's obviously lots of different cryptocurrencies out there. I think some are taking it seriously. Others are somewhat oblivious to it. So they should really start putting in a roadmap and a plan now for when Q-Day does arrive.
Right. I'd like to talk a bit about the geography of quantum. I mean, in Europe, we had a several governments who are very kind of forward-looking on this, and as you're saying, kind of put a lot of money into early-stage research and built up expertise, knowledge in this area. The Americans are now being very kind of capital-intensive and throwing money at it and kind of taking the lead. And the Chinese, at the state level, have decreed that quantum is an incredibly critical industry and are putting a lot of money into that, and we don't really know at what stage they are. So who's going to win this kind of quantum race, do you think?
Yeah, so I think if you look across the quantum landscape, Europe traditionally has been very, very strong in the R&D and in the academics, and the European governments were very pioneering in really bringing quantum out of the research lab and understanding and developing these paths towards quantum computing. But it's really in the US is where people have been able to scale up the technology. Like from my own personal perspective, it was 4 British founders from the universities of Bristol Imperial that we came up with the idea of PsiQuantum, but it was only really in the US that we were able to get the funding back in 2015 to really scale up this technology. And if you look at the top 10 quantum computing companies in the world, maybe 1 or 2 of those are European, but the rest are all United States based. Mm-hmm. So I think that's the sad reality of the fact right now is that the scale up it's happening, it's happened. Those large companies are pushing forward at increasing speed with increasing capital behind them, and one of those companies will dominate and build the world's first large-scale quantum computing.
So is your sense that there are many quantum computing companies in Europe? Are their most likely exit is to be bought by one of the giant American companies?
I think we're already seeing that happen. There was a great example in the UK where Oxford Ionics was bought recently by IonQ. So I think we're already starting to see leading expertise in Europe being brought up by American companies. But what I fully expect to happen, this is the dawn of a new age of information technologies. Just like with AI is dominated by the American companies. But there are many, many, many opportunities as to how you can use AI, how you can create startups that leverage this new technology. And I fully expect the same to happen with quantum.
And China?
China, we really don't know much about what's happening in China. We do know that they have an incredible R&D effort. They have very, very strongly backed government activities. Something estimate of about $10 billion US dollars has gone into academic and startup activities in China. Some of my best PhD students from when I was at Bristol, a professor at Bristol, were Chinese and have gone back to China. So they have incredible talent out there. Mm-hmm. So we should be wary and we should watch them closely. Without doubt, they will build a quantum computer.
Right. Final question. There's been a huge amount of talk at this conference about AI and the impact it's going to have on all kinds of industries and every aspect of our lives. But you think quantum is going to have a bigger impact?
I think quantum, it allows us to compute in a way that has never been possible before, that has an exponential power. And it's just hard to get your head around what that means, but it's just going to massively unlock humanity's potential to innovate, to discover, to design in the physical world in which we live, we work, we play. And I think if we look back 1,000 years' time, humanity looks back on this era, I think they'll see AI as a little blip in comparison to what quantum will enable us to do. If we ever get visited by aliens, those aliens will have created quantum computers centuries before that will have enabled them to create the technologies to come and visit us. And I think that's what quantum computing will enable for humanity.
So there we have it. AI is a little blip in... so puts things in a different perspective. But Mark, thank you very much for a great talk.
Thank you very much. My pleasure.